Oh, hello and welcome. This is SFU Math 232. My name's Brenna Davison. We are looking here at section 5.4. So last lecture, 5.1, we saw an application of linear algebra, the Markov chain. And now we're going to just see another application, the power method. And this is somewhat, well, it's an introduction anyhow to how internet search engines work. So the basic idea here is that we can use a method other than the one, for example, so how do we normally find determinants? Sorry, let's try again. How do we normally find eigenvalues and eigenvectors? We have been taking the determinant of lambda I minus a, getting the characteristic polynomial, and then finding what are the eigenvalues. Okay, this method is very slow for large matrices. Basically, do cofactor expansion to find the determinant. So it's an ON factorial problem, and then you've got a polynomial that you need to factor. That's also problematic. And so we're going to look here at a different way of finding at least the dominant eigenvalue of a matrix without computing a determinant. That's the idea. And then you can use that on matrices that are telling you something about the way links are between different websites and which one you should look to first as being the sort of most important of the websites. Okay, so that's where we're at here. A little bit of a taste of this. I'm also going to send you out an article called the $25 billion eigenvector, and that is an article that gives you some more detail. Okay, so here we are. So in many applications, we consider, like we just did in the last lecture, we're considering a sequence obtained by multiplying a vector, there it is, by successive powers of the matrix. And we saw that under some conditions that the vector converges to something. Okay, so we had that situation like this. We had x0, and then we were computing x1 as a times x0, and then we computed x2 as a times x1, which is in fact a squared x0. And we could continue like that. And we under certain conditions, this thing converged to a particular vector. And we called this the power sequence generated by A. Okay, so here's a statement. If the distinct eigenvectors of a matrix can be arranged in this manner so that there is one of them that is bigger than all the others in absolute value. So note the absolute value signs. Then that one that is the biggest of all of them in absolute value is called the dominant eigenvalue. Okay, so any eigenvector that corresponds to the dominant eigenvalue is called the dominant eigenvector. Okay, so let's just take a look at this to make sure that we understand what that means. A couple of extra simple matrices, A and B. Let us just notice what the eigenvalues are. Now, A is it's a diagonal matrix, so it's upper and lower triangular, and we know that for those type of matrices that the eigenvalues are on the diagonal. Okay, so it's not hard to compute what they are. So let us take a look at A for matrix A. The eigenvalues are those entries. The eigenvalues are this. Lambda 1 is 2, lambda 2 is minus 3, and lambda 3 is 1. So we've got 3 eigenvalues, and minus 3 is the dominant eigenvalue, because in absolute value it is the biggest. Okay, because we have because the absolute value of minus 3 is bigger than the absolute value of 2, and the absolute value of minus 3 is bigger than the absolute value of 1. Okay, so minus 3 is the dominant eigenvalue. Okay, so that's just another one for B. What are the eigenvalues? That's another nice matrix. We've got 3 eigenvalues. There they are. like that, and there is no dominant eigenvalue. Okay, there isn't one in absolute value bigger than all the other ones. Okay, because we basically have that the absolute value of lambda 1 is equal to the absolute value of lambda 2. So we do not have a dominant eigenvalue. Okay, with that definition in hand, we will move on to what's called the power method. So here's the theorem. A is going to be a symmetric matrix. Okay, there are powerful convergence results that apply to symmetric matrices. Symmetric matrices have n distinct eigenvalues. So there's a good reason why this is here, and also it's not as much of a restriction as you might think, because these symmetric matrices actually come up in the type of applications that we're trying to solve. Okay, so we're here. We've got a symmetric matrix, and it's got a positive dominant eigenvalue. Okay, and so then if we take a vector that's not orthogonal to the eigenspace corresponding to lambda, well, I'll mention more what that is later, and then we form this power sequence here. We start with this vector that we select, x naught, and then we form x1 from x naught in this manner right here. So we basically form x1 by multiplying a times x naught, and then what's here in the denominator is a normalization to keep the length of the vector to 1. So each time you renormalize to keep the length of your vector to 1. And then you produce this chain of vectors. And the theorem is telling us that this list of vectors will converge to the dominant eigenvector. Okay, so notice we have found a determinant at all. So we just sort of randomly pick a unit vector, and then we are able to do these computations, and we can find out what that dominant eigenvector is. And further, we can also, by taking this dot product, well, we take the we go along here, and as we go as far as we need to, and then we this thing here, this dot product, converges to the dominant eigenvalue. Okay, so first of all, I want to take a look here at how we could rewrite this sequence. So we have here x naught. We start with x naught, and then we're computing x1 like this. x1 is ax naught divided by the norm of ax naught. And then we compute x2, and x2 is ax1 divided by the norm of ax1. Okay, now what I'm going to do is I already know what x1 is, so I've got x1 right here and right here. So I'm going to replace x1 with what I already know it is. Let me just put that here. So x1 is here. So what I want to do is take this value of x1, this guy right here, I guess, and I want to substitute it in there and in here. So that's what I'm going to do. And that will give me that x2 is a times x1. And what is x1? Ax naught over the norm of ax naught. And then I have the norm of a times x1, which is ax naught over the norm of ax naught. There, looks a bit complicated, but it's not so bad like that. Okay, so then I can do some simplifying here. That's going to be a squared x naught. That is this times this. And then in the denominator, I have this here, the norm of a squared x naught divided by the norm of ax naught. And then I have here multiplied by the norm of ax naught. Okay, now these two things can be crossed out because they are simply a number. So that number is just a constant, and you can move it out if you're thinking of that computation of the norm as the sum of the squares of the components of the vector, and then you take the square root, you can factor that constant factor out. So that allows for that cancellation there, and that allows us to then write this like this: a squared x naught divided by of a squared x naught. Okay, so that's a nice feature, because then we can write out the sequence of vectors that we're going to get in this way, and they will look like this. That'll be the norm of a x naught, and then the next one, x2, will be what we just calculated. And then you could assure yourself by going through this process again if you like, but it is the case that you'll see that this one is 2, and that'll be squared like that, and then the next one will be cubed, and then it just makes a nice easy way of writing this calculation down. Okay, so we're going to get this sequence of vectors, and we're guaranteed by our theorem above that this thing here, as we go along computing it, this converges to the unit dominant eigenvector. Okay. All right, so let us just a little picture of what's happening here. We're dealing with unit vectors because we normalize at each step. So the vectors are, we're in R2, and the vectors are therefore in the unit circle. Okay, so we imagine the situation where we calculate the well, let us just say we're not going to calculate it. We're in the way, but it is the case that we have a 2 by 2 matrix here. It's got 2 eigenvalues, and so we have the eigenspace of each one of those. So let me just, for sake of argument, say that the eigenvector for lambda 1 would be right here. So I'm going to call that v1. Okay, and that means that this, like right through here, T v1, this line right here is the eigenspace of lambda 1. Okay, and then because our matrix is symmetric, okay, so this is important, A is symmetric, otherwise I wouldn't be able to say this. A is symmetric, so that means we've got distinct eigenvalues, and it also means that the eigenspaces are orthogonal. Okay. All right, so that means on my little drawing here, I can draw the other, it's going to be here at a right angle, down here like that. So that's intended to be a right angle right here. And so this here is T2 times V2, where V2 is the eigenvector corresponding to lambda 2. So this is the eigenspace of lambda 2. Okay, now we're just going to make an assumption. We're just going to assume that lambda 2 is the bigger. I mean, the same argument would apply. You just do it the other way. So I'm just going to assume that lambda 2 is our dominant eigenvalue. And then what we're being told here is by doing this sequence of events, going along like this, making these calculations, what we're doing is what we do is we select an x naught wherever we like, pretty much. Okay, we don't want to select it actually orthogonal to the dominant eigenvector, but that's okay. There's a few little details here, but what we want to do is just catch the idea here. So what we do is we select x naught, then we calculate x1, then we calculate x2, etc., etc., etc. And what happens is they move like this: x1, x2, x3, etc., closer, 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 until after a number of iterations, we are effectively here. So it converges onto there. So at that point, then we can figure out what that lambda 2 is and what v2 is without previously calculating the eigenvalue or the eigenvector. Okay, that is what this is about. That's the power method. Okay, there's a power method with Euclidean scaling, and that was based on that theorem that we based that on. That was when the dominant eigenvalue is positive. So let us just say here, actually really this is just a method, this is a writing out of the method in words. So what we're doing is we chose that arbitrary non-zero vector, we normalized it, and so we got x naught, and then we computed a first approximation to x naught, the dominant, x1 we calculated, which is a first approximation to the dominant eigenvector, and then we get that at the same time we get this. Then we get a second approximation to the eigenvector, and then we get a second approximation to the eigenvalue we're looking for. Okay, so the important point is we are not computing determinant of lambda I minus a to do this. Okay, so let's just take a look at a couple of steps. It's very difficult to do this stuff by hand because the calculations are numerous and it becomes laborious in an enormous hurry. So what I'm going to do is just show you how to calculate by hand, and then this one's a worked out example from the textbook, and then I'll show you like a whole bunch of numbers, and it's like then you can see it converging. But clearly you would just program a computer to do this. Okay, so first of all, let me just say we have A here, the matrix A. It is the case that the dominant eigenvector, which I'm going to call lambda 1, is 5. That is the dominant eigenvector. We don't necessarily know that starting this process, but I'm just saying because I just want to have this sitting here, so this is what I expect to find with this process. But because this is a small matrix, I can do this by hand. You could do this by yourself. Find the eigenvalues of this, and then you could find the corresponding eigenvector, which looks like this. Like that. And then if I want it to be normalized, if I want that the norm of v1 is equal to 1, then I select t equals to 1 over root 2. So the dominant unit eigenvector is 1 over root 2, 1 over root 2. Okay, so we know the answer that to which we are going, but now let us show how the power method comes up with that same answer. What happens? You take an arbitrary, okay, so now is the power method. Okay, I'm going to choose x naught. You pick an arbitrary vector of unit length, so there it is. Okay, then you compute ax naught, which looks like this, 3, 2, 2, 3, and you multiply by 0, 1, and you get this thing here, 3, 2. Then you have to normalize. So what you do is you figure out what the length of that thing is. So that's this calculation here. I'm taking the square root of 9 plus the square root of 3 squared plus 2 squared, and that is root 13. Okay, so then I have identified the first in my series of my sequence of vectors. It looks like that. There it is. Okay, so then I proceed on to get the next guy. That is multiply A multiplied by x1, which is 3 over root 13 and 2 over root 13. And what does that come out to? Oh, this is when you start praying you don't make any arithmetic mistakes, which is extremely easy to do. Okay, then I have to find the length of that vector, ax1, and that is root 13 squared plus 12 over root 13 squared, like that. And then I can write out what the next vector in my sequence of vectors is. It looks like this. There it is. Okay, and I'm basically going to give up because it's, right, for me to now go and calculate x3 by hand, it's just too much. Okay, so meanwhile, though, I can compute lambda 1 in this matter. So then I would take ax1, and I would take that dot product with x1, and that would be ax1 root 13, 12 over square root 13. I'll take the dot product with x1, which is 3 over root 13 and 2 over root 13, which I can compute it to be 3 plus 24 over 13, which is approximately 4.84. Okay, already I just want to point to something here. With this method, we have identified our lambda 1 here with this number here, and we know that at the end of this process we should be getting this here. Okay, so our first approximation to it is already, starting to be looking pretty reasonable. Okay, so what you now do is you go ahead and you just proceed with the numbers here, and that's what's here. Okay, so this is also in the textbook. So you applying this power method to a with x naught. So you calculate x1. There it is. That's what we found on the previous page. There it is with its decimal approximation. Then you use that to calculate x2. You proceed like that, and then in this model here, what has happened is you've gone through 5 iterations. At the same time, you do these dot products, and you get after 5 iterations you get that. So then this is your approximation of the dominant eigenvalue, and this is your approximation of the dominant eigenvector. And you can see they're quite close. I mean, we know that the exact value is 5 because we computed it, and we know that the exact value here, because we computed it, is 1 over root 2 and 1 over root 2. But not knowing that and proceeding with this method, after 5 iterations, we have this approximation for the dominant eigenvector, and we have this approximation for the dominant eigenvalue. Okay. The next point I think I'm going to make fairly quickly. Again, this is in the textbook. There is an alternate method. We used the Euclidean scaling where we divided by the norm. That can be a little bit slow because let's look what we have to do. We have to square everything and then add it together and then take the square root. So it's kind of nice to have a method that is faster, that allows you to scale to prevent these things from growing too large as you're doing the computation. So one way of doing that is the maximum entry scaling. That's the only thing that's different here. The whole procedure is the same, except rather than scaling by the norm here in the denominator, you're scaling by the maximum entry. So let's just do an example so we understand what the maximum entry is. It's not too confusing here. That is, imagine I have some vector that looks like this. 2 minus 3 minus 5 square root 2, say. And then I asked what is the max, like that. It's going to be 5. Okay, so it's in absolute value the largest number. I think that probably is said here. Yeah, here. Maximum absolute value of the entries in V. Okay, so exactly the same procedure. And then you simply keep going and going and going and going. And what we didn't say on the previous slide, but which applies there and it applies here, is that at some point you've calculated x1, you calculate x2, x3, x4, x5. You don't actually know, you don't in fact know what that dominant eigenvector is, but you've calculated x1, x2, x3, and then you think, when should I stop? I mean, so one stopping criteria would be to say, well, I'm going to stop once I don't see it changing very much anymore. So that's this method right here. You see very small changes going from one to the next one under some predetermined amount, a tolerance that you select in advance, and then you stop. Okay, so and then analysis can be done to determine how quickly, like how many of these calculations do you expect to have to do before you will get to where you want to be within a certain error tolerance. Okay, so I'm going to leave this here with really not too much said, and you need to look forward to taking MACM 316. That is where talking about how to what dropping criteria are, what error tolerances are, how fast do things converge. That is the course where that is taken up in much more detail. Okay, so this is not going to be, this is just sort of in some sense for completeness. We are not going to worry about this very much. Okay, so we get a sequence of vectors. Again, we could write them in the alternative way here, and that would look like this. AX naught over max. So this max AX naught calculation is faster than calculating the norm. And then X2 will be A squared X naught over max A squared X naught, etc. So we keep going like that, and they converge. So I'm just going to refer you here, page 254 in the Busby textbook. That is where there's a worked out example. Okay, Busby. All right, so how does this help us in the world of the internet? So we're going to just talk about a simplified version of the what's it called, hypertext induced topic search. It's similar to the PageRank algorithm. Of course, we're going to look at extremely small sample size. So basically what happens is you do a text search and you find where words are on a variety of different websites, and then you determine which websites link to other websites, and then what you want to do is determine, out of all these things that you found, which one do you show the person first? What is the dominant site? And because that you want to put at the top of your search criteria. So let us just imagine we have a internet consisting of 4 web pages. 4 and that's all. Okay, so we would have a page 1 here like this, page 1, and page 2 like that, page 3, and page 4. Those are our 4 websites. And then we do some sort of a search, and we notice that page 1 refers to page 3, and that is all. Then we notice that page 2 refers to page 1, and oh no, page 1 I'm going to have also referring to page 4. Page 2 referring, so the arrow, so the arrows are indicating it this way. Page 1 refers to page 4, like that. Page 1 refers to page 4. Page 1 refers to page 3. Page 2 is referring to page 1. I'm going to have page 3 referring back to page 1, page 3 referring to page 4, and then page 4 referring to page 3, and page 4 referring to page 2. Okay, and then we develop the adjacency matrix from that. Okay, so that is here. I'm thinking here of these numbers here, like this is page 1, 2, 3, and 4, page 1, 2, 3, and 4. So when I'm forming A, so this is, but the result of my text search. And then now I'm going to form a matrix to capture all of that information. It's an adjacency matrix. And so what does this mean? Well, first of all, page 1 doesn't refer to itself, so there's a 0 here. So then I'm looking across here, and I'm saying here, page 1 does page. So I'm starting here with page 1. Does page 1 reference page 1? No. Does page 1 reference page 2? No. Does page 1 reference page 3? Yes. Does page 1 reference page 4? Yes. Okay, so this one right here is a result of page 1 referencing page 3. That is this arrow right here. Okay, and I just go through the same thing. Does page 2 reference page 1? Yes. Does page 2 reference itself? No. Does page 2 reference page 3? No. Does it reference page 4? No. Okay, then I go to page 3, same thing. Does page 3 reference page 1? Yes. Does page 3 reference page 2? No. Does page 3 reference itself? No. Does page 3 reference page 4? Yes. And I look at page 4. Page 4 references 1, 2, 3, and doesn't reference itself. Okay, so then I have this adjacency matrix. That's it. I have captured that the text-based search into a matrix. Now I want to know is if when somebody has searched on these words, and I've come up with this situation, which of these 4 pages should I show them at the top of the search criteria? Let's see. Search for linear algebra is super interesting. Get tons and tons of results. Which one should I put at the top? Okay, in order to do this, what happens next is there are sort of 2 basic roles that a site is divided. Well, there are 2 different roles. It could be a hub. That means it links to many other sites. Or it can be an authority. That means it is linked by many other sites. Read these 2 things carefully. Make sure you understand which way that goes. Okay, so if we've got our matrix A, I'm just going to write it here again for convenience. We've got our matrix A, which looks like this: 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0. There it is. Okay, now we compute. We want to, okay, let's talk about the hubs first. And that is going to be the rows. So I'm looking here and I'm like, how many sites does site 1 link to? And that answer is 2. I add these 2 things together. So I'm going across on the rows and I'm thinking, okay, how many sites does site 1 link to? Site 1 links to 2 sites. Let's just scroll back up and see that in the picture. Site 1, page 1, links to 2 sites. There's 2 arrows. Got so many scribbling on here. It links to 2 sites, one right there and one right there. Okay, that is the sum of these 2 numbers right here. Okay, I'm back down here and I'm going to do that for all of them. I'm going to say I've just looked at site 1. Then I ask how many sites does site 2 link to. So I add up the numbers in that row and I get 1. And then I do the same thing here. I add up the numbers in that row and I get 2. And then for site 4, it links to 3. So site page 4 here, this guy, because that is the biggest number, that is a major hub. All right, this one here is the sum of the rows. Then I form an authority vector, and that is the sum of the columns, and that is how many people link to you. So you're an authority if many people refer to you, and that is the sum of the columns here. Okay, so now I'm looking at, for site 1, yeah, how many people refer to site 1? And in this case, so that is the sum of the numbers in the column. Refer back to the picture if you or draw the page 1, 2, 3, 4 thing here, and you can see it as well. Okay, so this I'm adding up the numbers in the columns. 3, 1, 2, 2. So this here tells me that site 1 is the greatest authority. All right. I'm still trying to decide which of the 4 sites should I show the person who searched on the words linear algebra as the greatest subject, right? Which of these 4 sites should I show them? Okay, so we want to order the sites by decreasing authority weight. So we want to know who's the best, really, is what we're asking. But we want to consider that if a site has a large if it has a large authority weight, then more hub weight should be given to the sites that link to it. And if a site has a large hub weight, then more authority should be given to each site that's linked by it. Okay, so think about these for a second, and maybe draw yourself a little schematic and say to yourself, okay, so if this site has a lot of authority, then when somebody links to that, that should be more valuable than if somebody links to a site with not much authority. Okay, so we then are going to update these vectors. This is our first pass at it. That's what we call H naught and A naught of the hub vector and the authority vector. So we take a first pass at it by doing these additions of the rows and columns, and then what we do is we have an update rule to accommodate these 2 things here, to try to get better information about who is likely to have the best information. So here is the update rule right here. Okay, we're calculating H1 and A1, and you will notice that I first calculate H1 here, and then this value of H1 is used right here to calculate A1. And then when I come back over here to calculate H2, H2 will be A times the vector A1 divided by A1. Okay, and then that A1 is this guy here. So that A1 is being put here, and then I would calculate A2, which is A transpose H2 over H2. Okay, and then so that is, then this number here is going to be inserted in there. Okay, so now I'm going to do the exact same thing. I'm going to keep going, and I'm going to calculate. I've started out with H naught, A naught. I'm going to do exactly the method we talked about in the beginning. Now I'm going to, except there's just 2 vectors now instead of 1. I'm going to calculate H1, A1, then I'm going to calculate H2, A2. And I can keep going like this. Now, I will then find that, so after, okay, so you can, with the example that we're using here, we started out with A naught, well, where is it there? A naught was 3122. Okay, and well, let's go down here and we'll see the calculation. So there's where we started, 3122, right here. That was our initial weighting there, and then we calculate out A1, and we find that we get this thing here, like that. That's our A1. That is our new authority weights. We can now calculate A2 if we want, but let us just say we were to stop here after 1 calculation, then we would be recommending, after seeing this, we would be recommending page 1 to the user first. We would then recommend page 3. Then we would recommend page 4, and then finally we would recommend page 2. Okay. All right. So let us take another look at these calculations. We see what we're going H1, A1, H2, A2 like that, but actually using a little bit of algebra, so we're starting like this. We started out with the A naught, H naught, and then we calculated H1, and then we calculated A1, then we calculated H2, and we're going like this. Okay, that is what we're doing. And we're going to use this to determine which, in what order should we show the pages to the user. And actually, you do not need to, the H can be, you can sort of substitute out through here, and you figure out that this can actually be calculated directly like this. So the kth version of the authority vector can be calculated like this. Okay, now what is really nice about this is we're using a power method, and what's really nice is the vector that we're using in this power method. As a result of having this sort of back and forth procedure happening, the matrix that we're using is A transpose A, and A transpose A is symmetric. So our theorem that we started with in the beginning, saying that if we have a symmetric matrix, we will converge onto the dominant eigenvector, it holds. That's what's so nice. Okay, so like really this algorithm is a power method with Euclidean scaling applied to the matrix A transpose A, where in this internet search idea, A is the adjacency matrix for your text-based search. Okay, so then after a while, we'll do these calculations, and AK at the end of this thing, when we decide to stop, AK will approximate the dominant eigenvector of A transpose A. Okay, so you notice that, I mean, with 4 pages, we had a 4x4 matrix, right? So I mean, there's a lot of pages on the internet. So your matrices are huge, meaning that you cannot compute the dominant eigenvector or the dominant eigenvalues by using the cofactor expansion. It's just too slow. So that's not going to happen. But you can do this, and what of course you want is for it to converge quite quickly. So what you do is you can run computing like this, run calculating like here. Well, you start out with A0, but then you calculate A1, and then you calculate A2, and you can go along like that until you get somewhere along the path, and you run until things are not changing much. So you notice, for example, AK plus 1 and AK are basically the same. And then you stop. And then you get some vector, like the one we looked at before, which was like this. So now imagine we have come to the place where things are not changing much. So we've converged to the dominant eigen vector. And then what we do is we order based on that. We're like, there's our number one recommendation. There's our number 2 recommendation. There's our number 3 recommendation, and there's our number 4 recommendation. So the bottom line of this lecture is just really a dipping our toes into this whole thing. But the really the big point is that you do not need to use the determinant in order to get at the dominant eigenvector of a symmetric matrix. This can be done iteratively. So that is our sort of introduction to this. So we're going to stop here, and then as part of when I send you guys some information, I'm going to send you an article called the $25 billion eigenvalue, where you can see that this idea and using it to quickly get very good search result recommendations was worth a lot of money. Okay, that's it for now. I'll be back with the next lecture shortly. Bye.